Hello everyone, my name is Hafiz Abid Qadeer, and today I am going to talk about LLVM in a bare metal environment. So in last year, I have been trying to build a LLVM bare metal toolchain that uses most of LLVM runtimes and is not dependent on GNU runtime libraries. And in this presentation, I am going to describe some of the things that I have learned during this process. So this is overview of the presentation. First, I will go through some background of bare metal. Then I will describe some of the challenges of building a bare metal toolchain, and then finally the results. So why is bare metal different? When we run a program on a typical operating system like Linux or Windows, we have operating system between the user program and the hardware. And the operating system provides us with a lot of services, like it loads our application. It provides dynamic linking support. It also provides us with thread and process control and file system and console I/O, apart from other things. But when we take the OS away and move on to a bare metal system, then our program is in direct control of the hardware. But on the other side, some of the services that were previously provided by the OS are no longer available. So we don't have dynamic linking, so we have to use the static linking and link all of our code and libraries into one executable. Your target may have customized memory layout, so you will have to use a linker script so that your linker can correctly generate an executable that will work on your hardware. You don't have any process or thread control, and similarly, you don't have any file system or console I/O. So your testing will be a bit different than what if we have a toolchain for a whole system. So what are the challenges of bare metal toolchain in LLVM? In my opinion, the biggest challenge probably is that there are not many bare metal LLVM toolchains around. So a lot of the code path don't get exercised enough. For example, look at baremetal.cpp. This file was added in 2017, and it has a small typo that .a was not needed. But this error did not get noticed, and it was only fixed 3 years later. Although it could have been quite obvious if you try to build a toolchain that was based on this file, and you will notice the problem when you try to link an application. So I think it is getting more traction, but still we don't have enough bare metal LLVM toolchains around. So these are some of the components that I will be discussing in this presentation. The compiler driver is responsible for finding the command line for different tools that will be invoked. Compiler proper will generate the code for your target. I assume that you already have a compiler that is working, so we will not go into this detail. Most of the time in the presentation will be spent on discussing building and testing of runtimes. And finally, we will discuss the link. So first we discuss Clang Driver. The responsibility of Clang Driver is to generate the command line for the different tools that are needed for the compilation and linking process. And it also needs to figure out the correct include and library paths and the libraries that needs to be linked. We have in Clang Driver bare metal.cpp, which is supposed to do this work. Currently, it only supports ARM, but as I've shown here, it is quite easy to add support for the target. You can have a function like is ARM bare metal, and it only checks that you have correct triple for your target. So it is quite trivial to add support for other targets too. But this file doesn't support Multilib. So if you want to support Multilibs for your target, then you will need to add support. Apart from bare metal CPP, some other toolchain like RISC-V does its own stuff, and it also have a bare metal toolchain, but that is dependent on GNU toolchain to be present. Now we come on to the runtime. And the runtime that we will be discussing is compiler RT, C library, and libc, libc++ ABI, and libc. So before we go to building the runtime, let's have a quick look at the build order. So first, you will need to build your host tools, like your Clang and your linker. At this stage, you need to make sure that in LLVM, you build the target that you are interested in. After this step, you will have a Clang that you can then use to build the runtime. Please note that you will be using the Clang that you have just built for building the runtimes, and not the original compiler that was used to build the Clang itself. So after the host tools, we will first build C library. And after we have built and installed the C library, we will move on to compiler RT. After compiler RT, we have enough stuff to have a C-only toolchain. For C++, we will need to build libc++ and other supporting libraries. So order we will follow is we will build and install libc++ header, then libc and libc++ ABI, and finally we will build libc++. So there are some CMake files in the repository that show how to do a unified build of the host tools and the target runtime. But I was not able to follow those examples for the bare metal target. For one thing, I was trying to build everything from scratch. I was not have any sysroot present, and it was not clear how to build compiler RT with different multilibs following those examples. In any case, I have found that it is more debuggable process to build the library standalone, and you are in better control of the process. So how do we build this library standalone? So I have shown the steps here. You go to a directory where you want to build. You invoke CMake, giving it the path of the library in the monorepo checkout. And what variable you will provide to CMake, we will discuss in a later slide. After CMake has done its stuff, then you can invoke typical make and make install. And if you want to test, then you can invoke some appropriate make check target. So this slide shows some of the common variables that will be needed by most of the libraries. In the first three are used to set your compiler. This will be the Clang that we just built. Then you will pass it the C flags and the CXX flags. This will include if you will specify your target, and if you have any target specific options, you will provide them here. Similarly, when you will be building multilibs, then you will also provide multilib specific options here. The last option I show proves useful sometime to avoid the link steps in CMake, because we are building the static library. So first I show the CMake variables which are relevant for compiler RT. The first one is compiler RT bare metal build. And this CMake variables help us select some source file for the build. Then compiler RT build CRT tells the CMake whether to build CRT files or not. This file include CRT begin, CRT end type files. Rest of the variables are quite self-explanatory. I was building only the built-ins in the compiler RT. So I have enabled the builds using compiler RT build built-ins, and the rest sanitizer, X-ray, and libfuzzer and profile are set to off. Similarly, for the lib and wind, I have lib and wind enable shared and libcxx enable shared. You need both of these two to make sure that shell libraries are not being built or being used in the testing. And then we have lib and wind is bare metal. This switches on some macros that are needed by the code. Then the next variables disable threading support. And last one tells the system to use compiler RT. Now we look at the CMake variables for libc++ ABI. Most of the first 5 of them are similar to what we saw in the previous slide. Then we have libcxx ABI enable exceptions that allows unwinding from exceptions. Then we have libcxx ABI, libcxx includes. If you remember the build order, I was first building the libcxx headers. So this variable will be set to the paths where those headers were installed. If we don't provide this variable, then the code looks at the headers available in the source checkout, and they may not be the correct because they have not been they don't have the correctly configured site config file, so they may cause some errors. And last one is libc ABI use LLVM unwinder. It will cause the LLVM unwinder used in the testing. And now we look at the CMake variables for the libc. Many of them are the similar as seen in the previous slides. libc enable monotonic clock needs to be off because threading is off. And then we use libc ABI. And finally, we set enable file system to off because my system didn't have support for the file system on the target. And when we use this variable and the common variables as I showed in an earlier slide, then should be able to build all these libraries. Now we look the layout or the directory layout, how it will look when we install these libraries. So we have two sets of libraries. One is which is dependent on compiler version, compiler RT. That is installed in a compiler version specific folder, as shown here, libclang, and then version, and then lib. And the final directory where the library file goes, it is named after the OS name, and that can be set by using CMake variable compiler RT OS dir. If it is not provided, then the system will pick the system name. On my Linux system, this directory is named Linux. The baremetal.cpp file expects that this directory will be named bare metal for bare metal target. But as I will show in the next slide, we probably will be better off naming it after a target triple for a bare metal. The next set of libraries are the C library and C++ library and all the other supporting libraries. They are generally put in a location which we can provide to the system using -sysroot flag. But one thing that is not clear is if the sysroot flag is not provided, where those libraries should go. Normally in a GNU toolchain, such libraries are placed in a top-level folder alongside bin and lib directory, and that directory is named after the target triple. One other thing to note is that there are other CMake variables that can affect the name and the directory of the destination directory of these libraries, and they are a cause of a bit of a confusion. So in the next slide, I will show the layout that I was using instead. So for the compiler RT, I was, instead of OS directory, I was naming the directory after the target triple. I think it will be much cleaner solution. For example, when we have different architectures and those different architectures have different multilibs, then all those multilib directories present in the bare metal will be cause of confusion and even probably will cause errors if the name clash. So it will be much better if we name the library after the target triple so that the different multilib directories can go into their own proper triple name directory. Similarly, The other libraries like your C library and C++ library, instead of putting into a top-level folder, I put that in Clang runtimes, and then a directory which is named after the target REPL, and it has include and lib directory where the file related to the libraries go, and the headers for the C library headers and C++ library headers will go. And I think this approach has some advantages for Clang. Instead of putting it in the library at the top level. For example, one thing is that Clang can support many different targets. So if we start putting this sysro directory in the top level folder, then it can crowd it out. There will be a lot of directories if we have supporting multiple toolchains. And the other thing is that our directory, the directory layout for a Clang sysroot may look a bit different than the directory layout of GNU sysroot for a bare metal target. And this will be cause of confusion if they are placed in the same location. As I will discuss in the later slide, when we discuss the bare metal, when we discuss Multilibs, that there are some issues how the files are laid out in GNU sysroot for a bare metal target that we can improve upon. So now we have discussed how to build and install the libraries. Let's discuss testing. So if you are familiar with LLVM testing, you will recognize that most of the LLVM tests look like this. We have run lines which run a tool to produce some output. Then you run another tool to dump that output, and then use file check to match the patterns that you expected in the output. And these tests can be run on the host. They don't require any target access, but they're only suitable for host tools. For target libraries, most of the tests are execution tests, so they need target access. But before we think about target access, we need some other things to be able to build test executable. And what are those things? We will need low-level library that will provide a starting point of our application. It probably will be written in assembly. It will do some basic initialization. Then it will call appropriate initialization routine. And then it will pass control to our main function. And when main returns, then it will wind down the application and somehow return the code back, return code back to the host. And apart from this low-level library, you may need a linker script to correctly generate your test application according to your target memory map. Apart from that, you will also need to define these symbols. These 4 symbols are shown here. They come from lib and wind. In case of bare metal, you need to define this, otherwise you will get some link errors. And they need to point to the start of each frame and end of each frame section. And similarly, the other 2 need to point to the start of each frame HDR section and each frame end of each frame HDR section. Once you have these 2 things and your user code and the libraries, you should be able to build test executable. And once we have executable, then it comes a time to run it on the target. libc uses a notion of executor that it will use for the target execution. Compiler RT similarly uses a notion of emulator, but they are quite the same thing. We discussed them in the next slide. So when compiler RT has a test executable ready to run on the target, it will invoke emulator like shown below. It will pass it the name of the test executable. Similarly, executor is also passed the name of the executable, but it also gets some extra parameters. But they have the same job, both of them. They need to somehow run the given executable on the target. So how they can do it, it depends on what target we are using. For example, if we were using simulator, then it is quite straightforward. For hardware, we may need to do a bit more work. For example, the target that I was using, I could connect it using a USB to my host system. And then if I run OpenOCD on my host system, it was able to connect to the board using the built-in JTAG. And that OpenOCD provided GDB server-like interface that my debugger can connect to. Then I can connect my debugger and load the memory with the bits from the executable, and then start the execution. So the implementation of this emulator executor will depend on your target. The next thing that it will need to do is pass the return code back to the testing infrastructure. And how it can get it? One technique that I used was that my exit function will print it on the serial port, and my host system then can read it from there. If your system supports semi-hosting, then it makes it much easier for the debugger to read the code, and you can then pass it back to your testing infrastructure. So these are some of the things that you need to do to implement emulator and executor. But the compiler RT and libc they don't need to worry about it. They just call these scripts, and they expect that they will do the job and return them the return code. And based on that return code, the testing infrastructure can decide whether the test has passed or failed. Now we look at compiler RT test case. If you look at it, it will look something like this. There is this run line that we are familiar with. The first part is trying to build a test executable, and second part is trying to run it. Using appropriate CMake variables, you could provide information to the testing infrastructure. For example, the percentage run thing is can be substituted with the emulator that you can provide with compiler RT emulator CMake variables. Similarly, if you need to provide certain compiler link variables, that you can provide them using the CMake variable compiler RT test compiler cflex. And if you provide the right information with these two variables, then you should be able to build a compiler RT test case. Now we look at the testing of libc++, and the same issues will also apply to libenwind and libc++ ABI. So some of the libc++ test will look the same as the test we have previously seen, which have run lines, but there are only very few of them. Most of the tests you will see don't have any run lines. And but what happens internally is that libc++ uses these two commands that I show here. First one it uses to build your test case, and second one is used for running the test case. And you can provide a lot of information which will be used when the testing infrastructure substitute these variables with concrete values. So we look what information we can provide. First one is the name of the test case. It tells the testing infrastructure what it needs to do. For example, if the name is foo.parse.cpp, it tells the testing infrastructure that the test case needs to compile, link, and run. If all the steps are successful, then the test is a pass. On the other hand, it can be foo.compile.fail.cpp. It means that we should expect the compilation step to fail. Similarly, you can say the name of the test file that it needs to compile and link but fail at the runtime. Apart from the name of the file, you can also provide the value of certain variables using CMake. For example, the percentage exit thing can be substituted with the executor, as we discussed before. We will later, in a later slide, look at some of the variables that are currently used. And finally, in a test file itself, you can use these two tags to provide more information to the testing infrastructure. One is the additional compile flag. It tells them that this specific test case need these extra compilation flag to successfully compile. And then also there is this file dependency things. This tells the testing infrastructure that you need to copy these files at the correct locations, but these are not relevant for the bare metal target, as we did not have any file system on the target. Before we discuss some of the customization that you can do, we first try to understand how the information passed through CMake variables reaches the testing infrastructure. So in your test folder, you will see that there is a cfg.in file, which describes some of the config variables that will be used by the testing. And this value of these variables depends on some of the CMake variables as shown in the example. And when user run the CMake, giving it the value of some of these variables, then CMake does its stuff, and it generates this lit.site.cfg file, which will have the correct value of these variables as passed by the user. So some value of some of these variables could be inferred by the CMake, or there are default values of some of the variables present. So if you need to provide some information to the testing, then you need to do two things. You need to have a CMake variable, and you also need to have corresponding entry in cfg.in file. Recently, I came to know that there is another way. Instead of relying on the cfg.in file that is present in the sources, you can have a totally customized cfg.in file that may reside outside of the tree. Then you can tell the CMake that instead of using the file inside the source tree, it can use this file by using libc test config variable. And CMake will do the same thing by using this file and generate your lit.site.cfg file. This thing provides quite a lot of power to the people who are working downstream, because they now don't have to worry about changing the cfg.in file in the sources of LLVM sources, but instead they can provide their own cfg.in file, which is customized for the target. So it is quite useful. There is a talk about libc++ testing, I think, later today, and we probably will know more about these changes in that talk. One other thing that I will want to point out is that, for example, you have run your test suite and you got your results, but now you need to run it on some other target that has the same architecture, but it has a different memory map. So maybe you need to use a different linker script, or maybe you need to use a different executor. So in our previous game, we will have to run the CMake so that we can provide the value of these variables. But if you are running LLVM lit directly, you don't need to do this. You can override the value of these variables by using the syntax as shown here. And you will need to know that the name of the config variable that this CMake variable corresponds to, and then you can override them on the command line. This facility is not available for compiler RT, where if you try to override some of the things like executor or the compile flags on the command line, it will still use the values that were given at the CMake time. I have a patch for review, and that should at least solve this issue for the emulator. And now we look at some of the CMake variables that are relevant for the testing. These are three sets of variables. One is for libcxs ABI, one for libcxs, and one for libunwine. One is used for setting the linker flag. Other is used to set the compiler flags. And the third one is to set the executor. Now we have looked at the testing. After you have run that test suits, you will find that not all the tests make sense for the bare metal target. Some of the tests will fail. For example, tests that open some files. Some tests are dependent on process control. They expect some KL or fork type API. And then if your C library has certain limitations, then that will also cause some of the tests to fail. For example, I was using Multilibs, and I found that there were some failures in some locales related tests and some white characters and strtold. This API had a problem, so I saw some failures in a related test. There were issues with double float related math functions too. So now we discuss Multilibs. Multilibs is a way that you can use the same toolchain for the different configuration of the same architecture. For example, if you look at ARM toolchain, ARM can have different modes. You can generate code for ARM mode or a thumb mode or different profiles of ARM chips or different floating point modes. Your compiler can probably generate code for all of these different configuration, but only compiler is not enough. You need to have runtime libraries that has been built for that specific configuration. And then you have a complete toolchain. So that's where the Multilib comes in. You build your runtimes for all those different configuration and put them in specific directories. And then later compiler can find those runtime from those directories based on what the compilation option it was given. So here I'm showing a code sorcery on toolchain. On the left side, you see the contents of its sysroot folder. You see a lot of different folders here. On the right side, I show what GCC prints when I give it dash print multilib switch. You see that first it prints the name of the directory, and then it prints the switch that was used to build the runtime for that specific configuration. So you can see that there are a lot of different options and a lot of different directories where those multilibs are placed. You can see the similar thing here for RISC-V GNU toolchain, where on the left side you see the directories, and the right side you see the switches that were used to the switches that were used to build that specific multilib. So now we understand what multilibs are. Let's discuss the multilib in Clang. So Clang has this multilib class that can be used to specify multilib. As is shown here on the left side picture, you give it two things. First is the name of the folder where the libraries will go. And on the right side, you provided a switch that will enable that specific multilib. The plus sign means that when this switch is given, then you should enable this multilib. You can also give an active sign that will work the opposite way. And then you can see that you can define two options for, I have seen defining two options for the MR switches, and I'm defining two options with MAIB's ABI switch. And then you can have different permutations. You can mix MR with some ABI options, and you can also filter out the options that are not valid. And if you do it correctly, then on the Clang command line, if you give it a -print multilib switch, then it will produce the similar output as we saw for the GCC case previously. On the left side, you see the directory name where the runtime will go. And on the right side, you see the switches that were used to build that specific multilib. Please note, this is just the code that I'm showing is just like one small part. You need to add some other logic to select multilib too. Okay, so now we understand what multilibs are. So how we will build all of our runtimes for these different options. So you will effectively do the same thing as we have done previously, but instead of building library one time, you will build it like a number of times depending on how multilibs you are. And you will go to a different directory for every multilib, and you give your CMake, giving it the appropriate options for that multilib, and then you do your typical make and make install steps. Your build order will be the same, but you will just build the library for all the multilibs as I showed in the previous slide. And then we come to the layout. You will have, before the final directory, you will have a multilib prefix directory in the path. And similarly for the compiler RT, your libraries will go in the directory which has a multilib prefix in. And here it becomes clear what I meant when I initially said that if instead of naming the directory on the target triple, if we just name it on like we name it bare metal or Linux, then it will be a confusing thing when we build a lot of multilib prefix directory inside it. So now we have discussed the runtimes. Let's discuss a linker. So this is the final thing that we need to build our executable for the target. The only important bit that is generally needed for the bare metal target is good linker script support. Previously, LLD used to have issues in this regard, but it has come a long way, and I was able to use most of my linker scripts, and I did not have much problems. There are certain syntax that work with the GNU LD, but not with LLD, but there are not many. One example that come to my mind was a tertiary operator causing symbol self-assignment. That was working correctly with GNU LD, but not with LLD. But that was, I think, only one or two cases that I saw. Otherwise, most of the script that I have are working. And the work that did, the result of it is LLVM toolchain that is now freely available. It is supports to Multilibs, and it has been tested on Hi5 Unleashed board. So if you are interested, please download and have a look. And also, I will be upstreaming my patches. It will be great to have your feedback on those patches as well. And this brings us to the end of my presentation. Thanks for listening, and I will be happy to answer if you have some questions. Thanks again.
This Abid Qadeer, who just gave the presentation on embedded capabilities in LLVM. He's a member of the Sorcery Tools team at Mentor, a Siemens business. And my name is Catherine Moore. I'll be moderating this session. And I also work at Mentor as a project manager in the Sorcery Tools group. So it looks like there were quite a few questions asked during the session. I will be reading the questions to Abid, and hopefully we can get to everybody in the time that we have left. Let's see, Abid, could you explain the limitation which exists for cross-compiling MIPS and RISC-V targets? Let's see, I'm missing a part of that question. Were you able to get everything that you needed in GCC's toolchain?
I I'm not fully clear what's being asked, but for the RISC-V toolchain, I was able to get almost all the GCC dependency out. We only needed a C library for which we used Multilib. Otherwise, we were not using any of GCC's runtime or GCC system.
Okay. Next question, is compiler RT always needed, or in theory, libgcc from an ARM? That question just disappeared before I sort of before I asked it. I'm so sorry. I lost the second half of the question. Let's try something else. Did you use LLDB in this project? And if not, why?
So I was using RISC-V as my target, and at the time of the project, it was not supported in LLDB, although there was a patch out that added that support. So I had to use GDB, but I tried to use LLDB with that patch, and I found that connecting LLDB with Chemo or the GDB stub that was provided by the OpenOCD had little problems. So there were small modification needed sometime in Chemo, sometime in LLDB to make it really work. But I was mostly using GDB for my testing.
Okay. Do you have any plans to make LLVM libc usable for RISC-V?
Yes, I have some plans. As I said, the modification needed were not great, so I plan to get those patches upstream, so then people should be able to use LLDB with these embedded targets and Chemo.
Okay. Is there a public domain project that uses LLVM in a bare metal environment that you could recommend for reference?
I am not aware any target that is currently using LLVM bare metal toolchain. One of the reasons can be that there are not many LLVM bare metal toolchains around, as I described in my presentation. So once we have more of LLVM bare metal toolchain, and then probably the projects will start using it.
Okay. Here's another question. The GCC support spec file is very helpful in bare metal toolchains. For example, giving specs equals nano specs to change the library. Does Clang support a similar mechanism?
I am not aware of that. If there is any such support, even for like a multilib, you have to describe them inside the source code. You can't do it like outside of source code, as probably you can do in GCC.
I don't think you can do that, but were you aware of the LLVM enable runtimes configuration used to build runtimes with the just built compiler?
Yes, I was aware of that. There are actually some CMake cache files available in the repository that uses that option, and I briefly mentioned those in the presentation. But my experience of using those was that you could build built-ins and compiler RT correctly, but when it went to building the C++ library, then I had some problem with those options, especially when I was building the runtimes with multiple multilibs.
Okay. You mentioned using newlib as the C library. Could you please describe your experience with building newlib with Clang?
For RISC-V, it proved to be quite straightforward. Newlib uses an atomic build system, so you have to provide the correct configuration files, and if you set those correctly, like using Clang, your compiler, then it worked without any problem. Although once I was trying it for ARM, and I saw that there was some assembler syntax mismatch that Clang was complaining about, but it was some time ago. Probably that problem probably have been solved in newlib or Clang. And the other thing with newlib is that it can actually check which multilib your compiler supports, and can its build system can build all of them in one go. So that is quite useful.
All right, thank you. I think the question from before popped back up, so we'll try again. Is compiler RT always needed, or in theory, libgc from an ARM bare metal GCC toolchain could be used? Same question regarding libc++ and a C++ library provided by a GCC toolchain.
Yeah, this question has also been answered by the John on the chat window. So you could use libgcc as well, and similarly you can also use GCC's I mean std libc++ with Clang too.
Okay. And then what about the linkers capabilities? Only GNU-LD has a capability of linking bootloader with a custom kernel. Is this talk expected to cover kernel mode and user stuff for, I guess, example? That question was cut off, but.
This talk was about bare metal targets where we don't have an OS. I'm not aware what exact linker limitation are being asked in this question, but as I described in the talk, that I found that there are certain missing features regarding linker scripts that are still not present in LLV, which are present in GNU. Then there are some architecture-specific limitations also, like, for example, with RISC-V, I found that GNU-LD can handle the weak undefined symbols better than LLD. But as such, I did not find any limitation that were like really roadblockers.
Okay.
At least for my test cases.
Okay. Well, I think that's it for the questions that we have today. If there are any other questions, please enter them into the chat window. Otherwise, I think we'll wrap up for now. Thank you, everybody, for attending. Thank you, Abid, for the talk.
Thank you.